like to thank Annette for inviting me here. And I will speak to you about my most recent point of view on ICSM superconductors. So my point of view has been changing with experiments. I'm not a religious man, and I like to change idea. And so perhaps you will hear something new today than what you expect. Because we did some more experiments that shed some light on all the story. And what we want to see is to look all the 110 years of 101 year of superconductivity, looking for something like that. What is the maximum DC in a system made up of a single element? And the maximum DC is a niobium with 9.2, but under pressure you get to 20 Kelvin, also in the lithium under pressure. So if you change, you have about 100 elements, and you have to select one of them. But let's not only select one of them, but also the lattice structure, because when you apply pressure, the superconducting chemistry. If you go to binary system, the maximum DC is a niobium diboride, and it gets up. And if you go select binary system, then you can produce about 10 to 4 different compounds. But only one, magnesium diboride, got the maximum DC. If you go to ternary compound, the maximum DC is the tertiary compound. The maximum DC is around 2 copper 4 with about 50 Kelvin if you modulate the lattice structure by Lifshitz strain and so on. If you go to, but now the number of compounds you can produce is huge, but only one has 50 Kelvin. The same when you go to quaternary compounds, then you get 100 Kelvin. And the only one, IPCO, that is a very strange lattice structure. IPCO is a really fantastic material. And then if you want to get 130, and then you have to go to pentanary compound. When you go to pentanary compound, the number of elements is so large that you can make a huge number of compounds. Only one we know is 100. So if you look to ITC, from the point of view of material science of complexity, you have to increase the number of elements. And if you take a biological cell, and you have about 20 amino acids, 4. So you have about a number of about 200 and more components. And you can make a lot of systems with 100 components. And what happened in this case is that when you increase the number of elements, different elements, the entropy decreases. Because each element now is indistinguishable from the other one, and then people can get interaction all with friends. For example, we have got a module of lattice effects in ICSM superconductor, and we make a small cluster, and entropy decreases because now we have a section here in lattice, we have a section there in disorder, and then the entropy decreases. Why? Because we have distinguishable particles. No more undistinguishable particle, but distinguishable particle. And when we have more distinguishable particle, the entropy decreases. Up to a biological cell that is made by 100 of elements with fantastic coherence. Okay, now we know the story. What happened when we increase the element in a material? We start to produce modules. So the atoms not make a bond with any one of the other 5 different, but start to make bonds with the only preferred one. For example, take copper oxide, you take copper oxide and lanthanum oxide, so you make 2 different modules, and different modules create very strange heterostructure. For example, layers of magnesium, of boron, layers of neodymium oxide, and so on. So you have separated materials, and when you go to, for example, the pentanary compound, you have a huge. So this is the point that I showed to you today. Is essential. You can see really in the history. In the history, in the first 20 years, people started elements, then alloys, and then heterostructures. What's mean heterostructure? Heterostructure means that you have modules. Okay, so then you have modules. So you have the modulus of copper oxide with different intercalation compound, modulus of iron arsenide, and so on. So you see a different kind of modules, and these modules are arranged in a superlattices. As the number of elements increase and the complexity of material increase, LTC increase. This is clear. Take nights. So if you increase the number of elements, the number of module increase, LTC increase. So there is a completely change of paradigm. There is no more the interaction that drives IPC. There is not the interaction, is not more important magnetic or Coulomb or lattice, but this important is the lattice structure. So the lattice structure is what is determinant physics. There is no way of avoiding this point of view that I would like to share with you. In 1993, we just proposed the fact that some particular heterostructure can drive only ITC. And it was presented in 93. We made several papers and patents. It's clear that all ITC should have some heterostructures. And actually, superlattice of layers have been found in diborates, pycnites, and graphite intercalated compound, and also in the others. So this is really the way to understand these materials. So it's theory in 1980 in science, the theory of quantum mechanics reached a very high level, and the people of theory started to organize Institute of Theoretical Physics. This was about the 1980s. In 1980s, people were so fond of the theory that we have in classical and quantum mechanics, the theory started to think that there is no more need for experiments because the theory is so strong. And they can include the interaction with computers, now they can go everywhere and so on. But there was a problem, a paradigm of simplicity. So the paradigm that the system should be homogeneous. You can put all kind of interactions, magnetic, lattice, spin, and everything, but the system is homogeneous, or completely disordered, or a perfect crystal, or perfectly disordered. So a perfectly classified. Something intermediate with modules created where you have many components was about of this any of the field of theoretical physics. Only in Russia, I think, with Nagev and group was some people thinking in this. And it's also strange because if you take all the interesting electronic properties of material like silicon, you have to put dopants in order to have interesting properties. And but the dopants were not considered to be completely homogeneous distribution. So let us go back now to today. In today we know that you have this kind of modules, there's no doubt. And when you put together these modules, now you have a lattice misfit between them. So when you have a modulus of here a group and another group, we can have a misfit, these original works. So when you have a lattice misfit between two groups, then you start to have and then you want to put together the two. Then they can adjust or not. They can make peace by some compromise. And so one gets compressed and one gets expanded, and they should get an agreement. If you want the material, this agreement should be there. Then you can put all the cuprates. All the cuprates share a common group, a common module. The module is copper O2. Copper O2 is an equilibrium distance. There are 20 years of works for copper-oxygen bond and in the X-ups and short range orbit, and the reply is 1.97 angstrom. So 197 micrometer, plus or minus 1. Look now the copper-oxygen bond, the module of copper-oxygen bond in all materials. 197, the equilibrium distance is here. And so in all materials, these are all ITC superconductors. You have more than 100 samples. I plotted C3 copper-oxygen bond and TC. I don't care anything, doping, everything, disorder and so on. You put all like these superconductors. Forget everything. Just you give me one sample, I ask you copper oxygen bond, and measure by X-rays, by anomalous diffraction, resonance with many methods. And then this is, for example, strontium lanthanum quantum rays, these are mercury, then okay. Then it's clear that you have the module of a copper oxygen lattice is compressed, nothing below 185. So too much compression, there is no agreement. They cannot have compensated structures. And then you see that you have one optimum compression that makes it ICSM. It's the most fundamental. And when you plot this, then you also have to look to the lattice. Is the lattice tetrahedral or orthonomic? Any kind of orthomicity. And you see that exactly at the point of maximum TC, you have a broken symmetry from tetrahedral to orthonomic lattice. It can be in copper oxygen diagonal, but don't look like it. Why? Because the misfit broke not only the local symmetry, but also the long range symmetry. What to do the misfit strain? Misfit strain uses a corrugation of copper. This was a beautiful work we did in 96. Copper is corrugated, and the corrugation of copper is even bigger than the corrugation of oxygen in the other layers. Each module has a different misfit strain, so each module has a different corrugation. Okay, that was the second discovery that Mousse de Leon presented before me, and they found first in ICO materials. When they have this compression, the system make a homogeneous compression, or you have again phase separation. You have again the formation of modules. And that's kind of the idea of Alex and that actually when you have a polaronic interaction in a different strained material, you can have a module of distorted lattice and a module of undistorted lattice. And this was our discovery in 92 of the stripes scenario. The real original first stripes scenario is a scenario not of spin and charge, but distorted and distorted lattice. Two different metals. These are two metals. There is not antiferromagnetic spin. There are two metals, one distorted, one undistorted. So it's a texture. It's a texture, it's a material texture. And this is true for all materials where compression is above the critical value for IPC. So the Servoyan-Teller boron produced this kind of phase separation between distorted lattice and distorted lattice. So this was achieved by Exat and by many other techniques, by Osbauer and Kushalev and Shengelai.